If a final metallic MEMS device is desired, a thin titanium seed layer is applied onto the substrate with a sputtering process. The titanium layer is then oxidized. This is done to provide a better surface for adhesion of the polymer resist later. This step is skipped if the final device is a polymer microstructure. The desired shape, typically rectangular or circular, depending on the type of mask and the design layout that is to be used for the exposure. The cut PMMA is then annealed in a vacuum oven at 110 degrees Celsius in a programmed sequence to remove any residual stress in the polymer sheet before it is glued onto the substrate. This step is critical as it will avoid future delamination issues from the substrate and prevents cracks forming in the resists. Once the PMMA sheet is annealed, it is now time to glue the annealed PMMA sheet onto the titanium oxide side of the substrate. Freshly prepared glue, a monomer of the methyl methacrylate, is applied onto the substrate and the PMMA sheet, then pressed onto the silicon with a custom-made compressed air pressing system. A thin layer of Kapton sheet is placed between the resist and the glass plate to avoid stiction issues while depressing. The sample is left under the press overnight. Under pressure, the monomer glue polymerizes and forms a nice glue layer attaching the PMMA sheet to the substrate. The glued PMMA is then thinned down to a custom thickness requirement with a fly cutting process that uses a diamond tip. A coarse cycle removes 100 micrometers PMMA from the top surface to bring it closer to the required thickness. A finishing cycle then buffs it up to bring the PMMA to the required thickness and to have a clear optical finish. The sample is now ready for exposure with the mask in the beamline. The mask is mounted on customized mask holders and is then loaded inside the experimental end station, the scanner, and bolted on with close proximity to the water-cooled copper ring. A thin layer of Kapton is used to cover the top of the polymer to act both as a pre-filter as well as a physical barrier in the event of unexpected foaming in the top surface and to protect the mask. Shims of precise thickness are then placed on the sample at predetermined locations to introduce a small proximity between the mask and the polymer surface. Typical proximity gaps range from 100 micrometers for micron-sized features to up to 1 millimeter for large millimeter-sized features. The sample is mounted in the sample holder inside the scanner. Once fixed, the sample stage is moved up and attached to the scanning stage that already has the mask mounted. When the required dose is applied onto the resist, the scanner finishes the exposure by shutting the beam passage to the sample and closing the vacuum valves, and preparing the sample stage for unloading the sample. When the scanner chamber is vented, the sample stage is moved down to unload the sample with the latent image of the mask features imprinted on them. Immediately after exposure, the sample is immersed in a pre-mixed developer solution to wash away the exposed areas of the resist to the X-ray beam. This process is time critical as the longer the sample sits outside after exposure, the harder it becomes for the exposed resist to be removed. The development process is finished by immersing the sample in a milder developing solution and finally in deionized water. At the end of the development process, a detailed inspection of the sample is undertaken to confirm the integrity of the pattern transfer and to look for defects from thermal or translation arising from relative motion between mask and substrate during exposure. If defects are identified, the causes for defects are characterized and the entire process fine-tuned to minimize and eventually eliminate the source of defects in subsequent runs. If no defects are detected, the sample is passed along to the metrology stage for imaging with a scanning electron microscope. Once imaged, the samples are ready for use if they are meant to be polymer microstructures. For metallic devices, the sample is passed along to subsequent electroplating processes using the metal seed layer to fill the voids with metal, typically nickel or copper. Once electroplated, the remaining polymer is removed through a flood exposure process followed by development. The seed layer is then removed by bombardment with argon ions inside.